Oh, it's so small. I'm sorry. Hi, everyone. Hi. So, who's afraid of machine learning? Anyone? Yeah? So, oh, it's not working. To be honest, I am, or I was. I'm Britt Barak. I'm a Google developer expert for Android, so not for machine learning and not for AI. And I'm not a data scientist. I certainly do not have a PhD in anything, I swear. And recently, everyone started talking about machine learning and AI, right? So all these buzzwords were all around the air, and I kind of didn't know what everyone's talking about. So I decided to create this talk, which is kind of how I wish this would have been explained to me. So I hope you would like it. And let's begin, but I have to fix it before, because then I would not be able to move. I know. Yay! So, human beings, since forever, have been fascinated about how nature works and how can they use it for their own benefits, right? For example, when humans wanted to create a machine that can fly, what did they use for inspiration? Birds, right. They used the chest and the wings of a bird in order to create airplanes. That's right. And when they wanted to create machines that can detect objects underwater where you barely can see, what did they use for inspiration? What? Bats. Yeah, they use bats and dolphins to create sonar system. That's right. And then, okay, this is a nice example. So this is a bullet train. It was made in Japan in the 1990s. And the thing that it's really fast, it could go up to 300 kilometers per hour. So it's very fast, but it was very, very loud. So when it went through tunnels, you could have heard it for kilometers away. So do you have any idea what scientists could use for inspiration to fix that, to fix the noise? Any ideas? You can guess. We're all friends. What do you think? Birds. Okay, so there's actually one type of bird, a special one, that is called a kingfisher. It is a cute one, a small one, looks like this. And the thing about the kingfisher is that it can go through the water, catch a fish, and then go up again and fly with barely making a splash in the water. So scientists use this bird and its beak and its head in order to fix the noise of the train. So that's pretty nice. And that's cool. And now when humans wanted to create machines that can learn, that can take a lot of data and make conclusions out of it, what do you think they can use for inspiration? Brains, right. That's true. So our brains have a lot of information. It is saved, the information is saved in the small particles called neurons. So the neurons are just bits of information, and we have a lot of those in our brain. Can someone guess how many? It's more than 1 million. Can you guess? 40 million? It's more than 40 million. Billions? All right, so it actually we have 100 billion neurons in our brain. How much is 100 billion? Well, if you take 100 billion pieces of paper and you stack them one on top of the other, it's going to get to 5,000 miles high, or it's more than 8.5 kilometers high, which is basically the distance between here and Los Angeles. So it's a lot. So all of those we have in our brain. Now, the thing is that one bit of information, you can think of it as like one letter inside a whole book, right? It doesn't mean so much. So in order for it to mean something, it has to have a certain context to it, right? So similar to letters inside a book, so the letters are connected to other letters to create words, and words are connected to other words to create sentences, and then they can make sense to us. The neurons actually like to be connected, physically connected to one another, in order to create this context, this knowledge, and not some just bits of information. Actually, one neuron has between 30,000 and 40,000, 30,000 and 40,000 connections to other neurons. And they are kind of connected in like communities or networks. So the same neurons are kind of connected to the other neurons. And they form communities. So we actually, on our brain, have communities for like each skill or a habit that we have. For example, we can have a network for playing a guitar, or a network for driving a car, or a network for developing for Android. So all of this we have in our brain, neural networks, or neurons communities. Now, when we learn something new, there is an actual physical connection, a new connection, or actually thousands of connections that are made in our brain, which is pretty crazy, I think. You can see it pretty good. I couldn't find something that is better resolution, but this is like real-time learning in our brain, where maybe you can see, maybe not, it's not that important, but like you can actually see two connections, synapses, that are being connected in real time when we learn something new. So I was kind of excited about it. I thought it's pretty amazing. And basically, this is how it works in our brain, in our actual brain. But when we try to make a machine to do it, we have to find some mechanical or artificial way to do the same process. So scientists, and there are many researchers that found a way to do it, inspired by our brain. And there are, of course, many ways to do it, and many, it goes very, very, very deep. What I do want to show today is like kind of it's going to be a high-level way, but there, of course, are many different ways to do the same thing. But we're going to see one way to do it, and it's going to be tangible enough so we can understand what's happening and how it kind of works. So let's start with an example. So I don't know about you, my favorite food is strawberries. So I wanted to create some app that can take an image of a strawberry and basically tells us if it's a strawberry or not a strawberry, it's a different kind of food. So let's basically see how the machine, or how the model that we can create would do that. So if you take an image of a strawberry and you give it to a baby, and you want to teach the baby, all right, this is a strawberry right now. It is like too complex and too like, it's too complex to just show it and tell it, okay, this is a strawberry. Like what you can learn from it, how you can actually describe and learn that this is indeed a strawberry. So what the baby, our brain, and actually the machine would do is to take this image and divide it, like process some properties of the image, right? So it's not just image, but it's a set of properties. For example, that it is red, that it has this seeds pattern, right? And then that it has these top leaves that are strawberry leaves. So what we're going to do now is to create a neural network or artificial neural network that corresponds to that. So as I told you, each neuron is just a bit of information. In our case, it would be just a number or a score for each one of these properties. right? So, for example, here, how much this image is red, how much does it have the seeds pattern, and how much are the top leaves are what I expect them to be. So I give each property a score, and then there's another layer of neurons, which are some mid-layer computation layer that does some computation for us. Let's see what it does. Let's take one example, one of the neurons, in order to just realize what it does. So remember I told you that we have connections between the neurons? In our brain, the connections can be a different thickness. It can be very thin or very thick to decide how much this information is important for the end result. In this case, we can't have like a real physical connection. So we have a weight represented by some kind of number, which I can just guess at first. Because at first, the baby doesn't really know how much the fact that this image is red, how much is it important for the end result for us to decide that this is a strawberry or not, right? We're not sure how much it is important. So at first I just guess numbers, which are the weights, the importance of each properties. So we decide that it is somewhat important for the image to be red. It is very important for her to have the city patterns, and the top leaves are important, but like not as much. And I just decide, just guess numbers, and I start computing. And now I want to create some kind of equation with the weights and the scores of the properties. So there are many equations that I can choose from. For this example, I choose a simple one. I choose a linear one, where I just multiply each score by the weight, right? So this is what we decide for this example. We just multiply each of them. We get some kind of a score at the end, 1.04. Shouldn't mean like anything in real life for us. Now, what I can do is I'll say, okay, let's tweak the number a little bit. So I can add a little bias. I just guess a bias at first. So I just guess a number and add it to the equation. And once again, get the final score, which I say, okay, this is a score for now for this computation. All right. So the same way we did that, we're actually going to do for each one of the other neurons on this layer. Now the weights are different, of course, so we get different numbers, even though we use the same properties. So we have these numbers of the mid-layer of the computation, and at the end, what do we want to achieve? What did we want to achieve at the end? A result, yeah, a result to understand if this is a strawberry or not, right? So we're going to have an output layer of neurons. Each one is corresponding to like the answer at the end, if this is a strawberry and not a strawberry at this case. So the same way we did the computation for the mid-layer, we're going to do like pretty much the same thing, but just a different equation. And at the end, we're going to get a score based on the weights and the scores of the previous layer. And we're going to get a score, which is currently a probability, for each answer. So in this case, the probability that this is a strawberry is 87%. Okay, this is what it means. So we say, okay, we're 87% sure that this image is a strawberry. This is what we can do. All right, so what happens if I run the same model, the same algorithm, with a different image, for example, with an apple right now? So we're going to do basically the same thing. We're going to extract the properties, the same properties that we saw before. So in this case, the apple is the image, is really red, that's true, but it doesn't have a city pattern, and the top leaves, well, it doesn't have a top leaves, right? So we're going to get different scores. So even that the weights would be the same, we're going to get different scores on the second layer, on the mid layer, for the computation. And of course, the output layer is going to be different. And in this case, we say, okay, right now, we're 80% sure that this is not a strawberry. Okay? Still with me? Yeah? Awesome. All right, so the goal is that I can basically give tons of different images, tons of different answers, and the model would run on these different images, and at the end, I'm going to tell it, yeah, you were right, this was a strawberry, or no, you were wrong, this is not. And I'm going to run it on lots of images, give it the end result, and what it's going to do is, remember all these numbers that I told you that I just guessed at first? So what the algorithm does is it can take this image, the numbers that I guessed, and tweak them a little bit in order to minimize the error. And so, instead of being able to say, okay, I'm 80% sure that this is a strawberry, I'd be able to say, okay, I am 97% sure that this is a strawberry now. All right, make sense? Yeah? Awesome. So this process of giving lots and lots and lots of data and end results and having the model tweaks the numbers in order to minimize the error at the end is called training. It's the same way that, it works kind of the same way as that we do training when we're learning how to play a guitar, and then we learn some new subtleties of how to do stuff and what's right and what's wrong. So it basically works the same. And the thing is that it takes a lot of time. It takes a lot of time. It takes a lot of data. So usually what we do is do it on a separate server. Right? We would never do it on like our small, tiny, low resources device, mobile device in our case. We would never do it there. So we want to do it beforehand on like large devices with lots of, or servers with lots of resources where we have a lot of time. So it would never be if we need to give the user, you know, the response or the result at real time. We would do it before. So this is basically called training. We would do it beforehand. Now, I want to tell you one more thing about this layer, the mid layer of the computation that I showed you before. I show you just one layer, right? Just one middle layer and computation layer. But usually in real life, things are a little bit more complex. So instead of one layer, we actually have multiple layers there. Each layer is going to be in charge of slightly a different thing. So the ones that are closer to the input are usually going to be in charge of processing processing a small corners or small lines or like very simple things. And as we go towards the output, each layer is going to be in charge of more complex stuff. So if the first one knows just how to identify small lines, the next one are going to be able to detect longer lines and like longer and more complex patterns maybe. And then the end ones, the ones that are closer to the output, is going to be able to detect maybe an eye, maybe a leaf, maybe very complex patterns. So this is basically how it goes. There are multiple layers there, but we don't very much care how many and how many of those we have. So we call all of these layers that does the computations a hidden layer. All right. Of course, after the training and after this whole process, our main goal is to be able to give the model, this algorithm, an image, any kind of image that it have never seen before in the training, and make it detect if this is a strawberry or a raspberry or an apple or whatever it is, image that you have never seen before. This is the end goal. Now, all of this job of creating the model and deciding on the equations and the weights and the algorithm and doing the training and giving the data and processing everything. So all of this job is done by a professional called data scientists. It's not so much for our for us as developers, as mobile developers. Of course you can learn it, but it's the same way as if, well, you can learn how to play chess. It's a different profession. which is super interesting. Of course, you can learn how to do it, but it's a whole different world. What we as developers are going to assume that we got as a present a model that has been trained, that is working, that can take an image and produce a result that we can trust. So we want to assume that. And we're going to use these models in our app. All right? So there are multiple ways how to create these models and train them and so on. We're going to talk about one platform that allows us to do it and allows the data scientists to do it, which is TensorFlow. So TensorFlow is an open source library, and it was used it was developed and is currently used by Google in multiple apps that we actually use nowadays, like the photos, like the inbox, everything that we know and love. And basically, a special thing about it as it is called that, it always says that it is flexible for scale. And what does that mean? It basically means that you can use the same model, so the same training and the same logic and everything. You can use the same thing, first of all, to have it run on one or multiple processing unit, like CPU or GPU, TPU. You can use it on one or more. And also you can use the same model on different platforms. So on Android, on iOS, on different embedded devices, on our servers, on our websites, which is very good for us. So let's say I want to create an app that actually takes this image of a strawberry and shows it to the user if this is a strawberry or not a strawberry. We want to do it with an app. Now, my first thought is, well, why have all the hassle? Why not just take the image, send it to the server, and have the server give us a result back of what we see in the image? So what do you think about that? Should I do that? Should I just send it to the server or not? No? Why not? Sorry? Okay, what's the problem with that? If I have a lot of images, what's going to be? Right, so first of all, it's going to be a lot of data. We talked about bandwidth, and we talked about the network, which is one of the top reasons for battery consumption, and also the bandwidth is like pretty expensive for some users. What else? Yes, you can go ahead and speak, feel free. Right, it takes time. It has latency. It takes time to send the image. The user has to sit and wait. It's not a very good experience. And also, well, if you think about it, what did I want to say? Well, we don't necessarily want to send all this data to the server, right? Well, first of all, what about the user's privacy? And what about security that we need to handle right now? And, well, basically there are tons of reasons why this is a good, it's a good experience. It can be a good experience and it can be a good solution, but we can do better. And having something local on our device that does not need the network and it can give faster results even in offline mode is it has lots of benefits, right? So in order to do that, we need to have some library that supports that can take the models that the data scientists developed and trained, and to have them in some way on our local devices. So TensorFlow, as I promised you, allows us to do it. There is a library called TensorFlow Mobile that can actually take the model, and it's cross-platforms, as we discussed, and allows us to use it on our devices. We can use it, there are many models that it supports, like speech recognition, images recognition, translations, voice recognition, it's many models that it currently supports. The thing about it is that it was very, very, very heavy. So the models were like, it could be like close to 100 megabytes of just the model itself, which is a lot for our apps. So it was very heavy, it was quite slow, and the upload time of the app was like quite slow, so it wasn't very much of like the optimal solution. So lately, another library, a separate library was released, currently still in developer mode, but pretty nice to use, which is called TensorFlow Lite, which basically like takes the models that we used on the TensorFlow Mobile and allows us to do heavy optimizations on them in order for us to be able to use them in proper mobile applications and with better performance. So it is lightweight, it is faster, it is still cross-platform, which is great for us once again. The thing about it that currently the models that it supports are less than the TensorFlow Mobile ones. So currently we have the mobile net and Inception v3, which can do image recognition, like our example. So MobileNet is a set of models that are basically made for mobile and embedded devices, so they're pretty small and quick, and we can use them to do our image recognition. Inception v3 does basically the same thing, although it is heavier and so more accurate. So it's like a trade-off for our app. And another model that it supports is the smart replies, which just takes text. It's like in your the smart replies on your inbox app. So it takes the text and suggests us replies or smart responses to the text, to the questions that we've been asked. So we can use those. Of course, you can take models from your own models that you've created on the TensorFlow Mobile. There are some scripts that you can run on them and some processes that you can do in order to process them to make them fit for TensorFlow Lite. The thing is that currently it doesn't support all operators. But this is kind of where we're going to go to. So in the future, the idea is for all of the models, instead of TensorFlow Mobile, to be in TensorFlow Lite. And therefore, I wanted to show you some example of like real code and how to integrate it into your app. So I kind of thought which one is is better for us to show an example for, and I decided to show it with TensorFlow Lite. First, because this is where we're going, and second, because it is a little bit more simpler to use. So I wanted to show an example with that, and if you understand the structure and how things work and the relationship and the logic, like the relationships between the different components, it would be quite easier for you to now know how to do it in TensorFlow Mobile. So I decided to show this example in TensorFlow Lite for the app that we saw before. So we have an app, we have an image of a strawberry. So this is your app that you already know how to write perfectly. And then what we want to do is take this image, realize if it's a strawberry or not a strawberry or what's going on there. So we're going to send the image to class that I'm going to write called image classifier. This is something that we write. We're going to send the image there, tell it, classifier, please classify this image for me, this bitmap for me. The image classifier will soon see how does its magic, and then returns us a label, so a string that we can present to the users and tell them what we see in the image. So this is basically what we're going to do. First thing, of course, that we need to do is to add the assets, right? Add the assets to our APK. There are two files that I need to add. One is the actual model, model that we're going to use. Currently, I'm just using MobileNet just for the example. Notice that it ends with .tflight. This means that this is a TensorFlow Lite model file. And the second thing, of course, is the labels, which is just a text file. So the labels, it's a simple text file. It looks like this. The thing is that it's human-readable labels. And, you know, TensorFlow, we saw before, it doesn't really know the human-readable labels. It just uses numbers, right, and the artificial neurons. So we'll have these labels, and we'll soon see what we were going to do with it. Next thing we need to do is to add TensorFlow Lite library to our project. So we just add the maven repository and add the dependency. It's no biggie. A thing that is super important to remember, like super important, is to ask not to compress the TF-Lite files. So all the TensorFlow files and models should not be compressed because we're going to need them. Memory mapped in order to actually use them, in order to actually run the models. So this is a very important thing to remember. And then let's create the image classifier class that we discussed. So what's going to happen there? The image classifier is going to be the only one who actually knows TensorFlow in our app. The only one. So of course, I'm going to need to have a reference to the TensorFlow interpreter. The interpreter member is pair model. So I have to load the model and give it to the reference. It is pair model, so if you're going to use multiple models in your app, you're going to have more references, each pair model. And how do we load the model that we just added to the asset? It's pretty simple, well, nothing very complex here. We just go to the assets, take the model with the model path that we gave before. We open an input stream, we create a channel, and we just create a memory map for the model, for the file. Nothing too crazy here. And this is the way we can actually use the model. Now, next thing we need to do is to load the labels, right? We have to load the labels that we also added as a file. Once again, nothing too complex here, but I want to be able to use the labels list. And I'll have to do the matching myself between the numbers and the scores that we get to the labels list. So I want it to be in an array list or something that it's like easy for me to use as a developer. So I'm going to use it. Remember, it's just a text file. Each line is a different label. So what I'm going to do is just go to the assets, create an input stream, and then just create a label, a reader, and iterate over the lines. Each line is a different label, and I'm just going to add the labels. I'm going to add the lines into my label list. Basically, that's it. Not so scary. So this is how we're going to create the label list. And let's see what we're going to need it for. So once again, TensorFlow does not know the human-readable labels and the human-readable strings. It doesn't mean anything to it. What we're going to get from TensorFlow, hope you remember, is just numbers, is a list of numbers, like the model that we saw before with the artificial neurons. It's just going to give us the numbers, which for me it's a probability for each label. I'll have to do the matching myself. So if I get the array of all the probabilities, by the index, I would need to say, okay, this probability belongs to this label. By the index. So this is something that we have to do. So what I'm going to do is to create a place to allocate a space in our memory for the probability array, because I don't want to allocate the space each and every time each and every time that I create, that I ask to classify an image, right? Because it makes no sense, and it's going to be like a lot slower. So I just allocate this space beforehand, and as I use the model, my input is going to appear here on this member. on this reference. All right. So we talked about the output and how am I going to see and calculate the output, but what about the input? So like TensorFlow doesn't really know human readable strings, it would be hard for him to just take an image, to take a bitmap and like do its magic. So what we're going to do is we have to convert the image into byte buffer of the pixels, and then we can actually process that. So we have to do it before. So what I'm going to do is to, once again, to allocate a space for the input, which I call it image data. It is a byte buffer. How much space do I need for an image? So if it's one image, I need how many pixels I have in the rows, how many pixels do I have in the columns, right? Times the size of the pixel. So the pixel size, usually it's 3 for RGB. And this space, I'm going to allocate it before. Once again, just in order for us to be more efficient. Now, last thing that is left for us to do right now is just to run the model, just to give it an image and to see what it has to say. What do we see in the image, right? So I'm going to create the classify method that would sit on the image classifier. What it's going to do, honestly, very simple. So it's going to get the bitmap, right, from the app. It's going to get the bitmap. And now we have to convert, as I told you, convert the bitmap into a byte buffer. We're going to convert the bitmap to a byte buffer and put the result in the image data, that we allocated beforehand. As I promised you, this is our input. It's going to all be there. How does it happen? It's not so complex. I just wanted to show you you kind of would know what's going on there. But basically, we're going to go to the bitmap, ask for the pixels, and put the pixels in the int values member here, parameter. And all that's left for us to do is just to iterate over all the pixels that are now on the int values. So I'm just going to iterate over the lines, over the rows and the columns. And for each one of them, just put the bytes in the image data. It's pretty simple. Not so scary. So after we converted the bitmap into a byte buffer, and we can use it, what's left for us to do is to take the model and ask it, all right, please run on this image data, or run on our input. So it's going to run, it's going to do the magic, it's going to do all this model with the artificial neurons that we saw before. So it's going to do this whole thing, and then the output is going to appear for us on the probability array. This is our output space, it's going to be there. So after that, we're going to have the probability array with all the probabilities, and as I told you before, all that's left for us to do is basically whatever we want to do with the output. So this is our output, we have the label list, and we just need to match them and do whatever we want. On my case, I just choose the top 3 labels and decided to show them on the screen. So these are the labels and the probability for each label, because this is what I decided to do. Okay, so basically this is what we want to do. So we won. And what's left for me to say to you that, well, machine learning, as we saw before, is a whole new world. So it's a whole new profession, a whole new world. There's a lot of to learn and to explore if you want to go to that place and learn how to be a data scientist. But hopefully also as mobile developers, I got you a little bit inspired today and not so afraid to try to do it yourself and maybe to think about some new ideas of how you can create a smarter app that can take a lot of data and make some conclusions that would benefit your users. If you want to learn some more about it, I have here some links. Of course, I'll share the presentations. The slides are on my Twitter account, so you can check those out. So there are a bunch of TensorFlow and code labs for TensorFlow in general and for TensorFlow Lite. Hopefully today I gave you some explanation about what's going on there. And Dr. Joe Dispenza is the one that it's a very inspirational person in my life, and I learned all this, the intro that I gave you about the brain stuff and how it works. So if you like this kind of stuff, you're very welcome to explore his talks, which are super interesting. And basically, this is it. So thank you so much. Here for questions. Here for questions, and keep in touch. Thank you.